Thanks a lot, and especially thank the organizers for inviting me here. This is my first time here. It's a very fantastic place. So I'll tell you about some work that I've done. My group, Nishita is a grad student in my group, and John was a grad student. He's a postdoc in Lausanne, and Matt Block, who is a postdoc with me, is now a faculty at Cal State. Okay, so I'm going to try and tell you about two things. I don't know if I'll actually manage, but if I get to the first thing, I'll be happy. Okay, so I'm very happy that Adi is sitting here because actually I learned a lot about anyons by reading your review articles. If you're a grad student, I can recommend it very strongly. It's a really beautifully written review article that explains things about anyons. So, one of the strange things about quantum mechanics in 2 dimensions is that you can have excitations which are not bosons or fermions. So if you think of this as a statistical mechanics problem, it's like it has a topological term. And you can show in 3 dimensions this topological angle is restricted to be 0 or pi, but in 2 dimension it can be, there's no restriction. Okay, so you can have these strange particles called anyons. And by way of introduction, we all know that these particles exist in quantum Hall systems. And this is a cartoon of a quantum Hall system and excitations, and when you exchange them, you get phases which are fractions of 2 pi. Okay, so the question is whether you can have anyons in other systems. So generally, you can't have them in systems which have product states, which have mean field states. You can show very simply that in such systems, the excitations are always either bosonic excitations. So there was this interesting idea that you've heard a lot about today and yesterday from this idea of the RVB wave function, where spin models can exist in wave functions which cannot be written simply in an unentangled way. In fact, they're quantum superpositions of many unentangled wave functions. The question is whether such systems can have anyonic excitations, and so there's been lots of ideas of this, starting with Laughlin and Kalmeyer in 1987. But really the thing that I think created a lot of excitement is Kitaev's work, which again has been reviewed so many times that I won't do it again, where you can get anyonic excitations, in particular this simple Z2-Topological order. Okay, so what I want to tell you about is, so I should say that there are also other models apart from Kitaev's model. There's Subhro had an old work, large N, on frustrated magnetism. There's a quantum dimer model by Mosner and Sondhi, and then there's a Balance-Fisher-Gerben model. There may be 1 or 2 other models I'm missing, but so we haven't realized the Z2 topological state in an experiment, and clearly it's of interest to find other microscopic models with the hope that this will be realized. So what I'll tell you about is a very simple, a very elementary microscopic model in which realizes the Z2 topological state. You cannot solve it exactly, but you can argue and study it numerically and show quite convincingly that it's a Z2 topological spin liquid. Okay, so this model is very simple, and I promise you that I can explain it to all of you in 5 minutes. Okay, so the idea is a quantum spin model. So a quantum spin model is a system in which every site has a finite Hilbert space, and the many-body Hilbert space can be created as a tensor product of the single body Hilbert space. And so, conventionally the single body Hilbert space, when you think of spin, you think of them as spin pointing up or down. But for pictorial purposes, I'll choose to represent the, the single site states by colors. Okay, so I imagine that I have colors. So I look at a lattice and I look at a particular spin configuration. It corresponds to assigning colors to every site. Okay, and the many-body Hilbert space is the number of colors raised to the number of sites. Okay, and this is exactly because there's no constraint in the Hilbert space, so it's not like a gauge theory or a dimer model. The many-body Hilbert space is a Kronecker product of the single-body Hilbert spaces. Okay, so here's the model. It's very simple. The idea is that you take 2 sites and you define a singlet. Okay, so the singlet wave function is defined as 1 on square root of n sum over equal colors. Okay, so this is so if you take so suppose I have 3 colors, blue, orange, and green. Then the singlet wave function would be just 1 over square root of 3 blue blue plus orange orange plus green green. Okay, so let's call this a singlet wave function. Again, the model very simply is given by the negative of the projector onto a singlet, and you sum over all bonds of the lattice. Okay, so this is a very elementary model. And it actually has a history that goes back to Ian Affleck and various other people who studied it. But the way I'm going to study it on non-bipartite lattices, and it turns out that most of the previous studies, or actually all of them, were on bipartite lattices. And it turns out that this difference is actually quite profound. It affects the phase diagram in a very, very central way, and I'll try and explain to you why that is. Okay? So let's just think about this model. So basically, you cannot solve this model exactly. Every pair of site would like to go into a singlet, but of course not every site can do it. So this might remind you a little bit of the quantum dimer model, but again, this is not a quantum dimer model, this is quantum spin model, because the Hilbert space is generated as a tensor product of the single sites. Okay, so you could have some state like this, but of course you could move these sites that want to go into singlets around, and so there can be quantum fluctuations. And so this reminds you a little bit of Anderson's RBB idea. Okay, so and so the question now is whether this model will actually go into the state like an RBB state, or will it crystallize so that the bonds form a valence bond solid. Okay, so just a few comments about the model. So again, this is if you think of the RBB wave function, this model looks very much like the RBB wave function. And again, unlike the quantum dimer model, what I'm calling a singlet is actually a spin wave function. So it's a singlet of a spin wave function. It's not a constrained model. So you could ask, what is the symmetry of the model? It turns out that the model has SON symmetry because you can rotate all the spins by an SON matrix. So this is where it's very different from the bipartite lattice. It turns out on the bipartite lattice, this model has SUN symmetry because you can multiply on one sublattice by an SUN matrix, on the other sublattice by the conjugate matrix. Okay. So apart from the sign, so this is interesting, this singlet, if I just summed over two colors and I put a sign between the two singlets, I'd get exactly the Heisenberg model. Again, it's very close to the Heisenberg model, but this sign is very important. This is where the word design of the design title comes from, is that we just decide to drop the sign. Okay, so that makes this model sort of tractable. So with the sign, of course, nobody knows on non-bipartite lattice what the ground states of this model is. There's a lot of discussion for the last 30 years, but if we make the small modification, it turns out that we can solve this problem. Exactly, and I'll show you that this model is so simple, it turns out that there are also possible physical places where it could be realized. Okay, so let's just think about this interaction. So if you expand the interaction in its basis, remember the singlet is a sum of equal colors. So this projector onto the singlet looks like 1 over n, sum on alpha beta, alpha goes to beta beta. Okay, so let's think a little bit about how this acts on the Hilbert space. So imagine that you take a state of your system. So basically, in order for this interaction to act, it has to take two sites which are the same color. So for instance, these two red sites, and then convert them to blue sites. The way it acts also is that because alpha and beta are summed unconditionally, if two sites are blue, they can decide to remain blue. Okay, so that's also allowed. So this is the way the Hamiltonian acts. And so now when you think about it, there are two competing tendencies. One is singlet formation, which we spoke about earlier. But another tendency is that the system wants all the sites to form the same color because then it can act maximally between all the sites. And so there's this competition between wanting to have all sites equal color and singlet formation. And actually this can be controlled by the number of colors in the system. Okay, so one way to understand that is to take this Hamiltonian and think of it as a transfer matrix and think of a StatMech problem in one higher dimension. Right? So if you take a Hamiltonian, you can think of a Euclidean action which it connects. And it turns out this Euclidean action has a very beautiful form. If you think about this, the way the Hamiltonian acts, it takes two sites with the same color and sends them to the same color. It takes two sites and switches their color at the same time. Right? So now if you think in imaginary time, the way this acts is it takes this model and in one higher dimension, it becomes a model of tightly packed loops. Okay? So you can convince yourself that if a loop enters here, there's basically nowhere for it to go, so these loops can't end. And so these loops have to close. So you have closed loops, and the thing that's very unique about these loops is they're tightly packed. Okay, so they're tightly packed because every link in space-time has to be attached to a loop. Okay, another feature is because this lattice is non-bipartite, you can't assign an orientation to the loops. Okay, so in this loop language, that's how the difference between the bipartite and non-bipartite lattice arises. So these are unoriented loops which are tightly packed. And it turns out that although we know a lot about loop models, these kind of loop models haven't been studied in a lot of detail until very recently. Right. Yeah. So it has one of these n colors, and so this is what shows you that when you make the number of colors very large, the system will want to go into a short loop phase because it gains entropy by doing that. Which is why at small n the system would like to be in a long loop phase, which is like a phase which breaks this SON symmetry, and at large n it goes into a short loop phase. Yeah, so it turns out that if you're trying to write a continuum field theory for it, it affects the way the continuum field theory is constructed, orientation. Well, it's just it's a different statistical mechanics problem. It turns out this orientation is sort of very relevant to its phase diagram. But yeah, you're right. But you're summing over loop configurations. You don't need to know about the fact of whether it's orientable or not. It matters a lot, yeah. Okay, so here's some of the things I just said. Okay, so we originally studied this model on the triangular lattice, but now for reasons that are of interest now, I'll tell you about our work on the Kagome lattice. So again, we can change, there's only one parameter in this model. It's the number of colors. So if I increase the number of colors, a very small number of colors, the system goes in the long loop phase. But if I make the number of colors large enough, the system actually stops to go into it. It goes, so if you, this is some measure of the loop length. I don't want to go into the details of what this is. But this shows that at n equals 9, the system starts going into a state with short loop phases. So in the short loop phase, you can think of the system as basically almost being in this situation where sites are paired and they're fluctuating between the pairs. And so now the question is whether this system will have an RBB-like phase where these pairs are resonating, or will it go to a state in which the pairs actually form a pattern and form a solid? Yeah, so sorry, yeah. So it turns out, so because of this, this minus sign over here, and because the minus sign in e to the minus beta h, each of these interactions actually comes with a plus sign. So this loop model can be interpreted just as a classical StatMech problem. And so you can update it very simply. You can recolor the loops, and you can join loops of equal colors to get new loops. You can show these are ergodic, and so you can sample this very efficiently with multiple. Okay, so yeah, so it turns out that so I said we can't solve this model, but there's one modification you can do to solve the model. So if you just make the number of colors large, you still can't solve the model. You can connect it to some other statistical mechanics model. But there's a limit which is very similar to what Arovas and Auerbach and then Reed and Sachdev did in 1989, which is that you think of this model, first of all, in terms of bosons. So you can write them as Schwinger bosons. And so that same interaction you can write down as a destruction of bosons of the same color and the creation of bosons of the same color. But then you require the number of bosons to be 1 to faithfully reproduce this model. Okay, so now what you can do is you can treat this number of bosons as an arbitrary parameter. It's like a representation of SON. And now if you increase this also as you take the large n limit, it turns out you can solve this model. Okay, so this is, again, people in the past did something very similar. So now you could ask, what is the phase diagram? You have number of bosons and you have a number of colors. And so, of course, with our Monte Carlo, we can simulate this number of bosons equals 1. But now we can, when you take the limit of both the number of bosons and n very large, you can solve it just with a saddle point. And so this is, again, very similar to what Reed and Sachdev did. The only difference now is because our lattice is non-bipartite, it turns out that you can't have this staggered assignment of charges. And so when you think about fluctuations around the saddle point, you have a U1 gauge theory, but that's coupled to a charge 2 field because there are two bosons, they both carry the same charge. So it's well known that if you take a U1 gauge theory and you have couple them to charge 2 bosons, you get a Z2 gauge theory left behind. This is work by Fradkin and Shankar. And so Shankar, no, not Shankar. And so as you tune this parameter kappa, which is the representation parameter. There are two phases, one in which the boson has a mass and the other where it condenses. When it condenses, you have what in the loop model would be a long loop phase. But when it has a gap, this argument suggests that you should have a Z2 quantum spin liquid. Okay, so this is the sort of field theoretic argument that at least at large n, here you have a quadrupolar phase and here you should have a Z2 spin liquid. And so by continuity, if we look at our model over here, this phase transition, it seems, since we already have this quadrupolar phase, it seems natural that this disordered phase is a Z2 spin liquid. So, but we'd like to establish that directly. So it turns out also that, if you just, this is also there in Reed and such, there was another paper, I think the nuclear physics P paper, where they show that if you just take the large n limit and you fix NB, you get a quantum dimer model. And the same is over here, so you get a quantum dimer model on the Kagome lattice. Unfortunately, you can't solve that model, but there is one solvable model of a quantum dimer model in the Kagome lattice, which also goes into the Z2 spin liquid phase. So it's consistent that basically even at large n, the system will always stay in this disordered phase. Yeah, but we want direct numerical evidence that this is a Z2 quantum spin liquid. And so, there are these interesting excitations, and unfortunately in Monte Carlo, we can't study the anionic excitations. But as you all know, there's a very interesting result that you can actually measure this thing called entanglement entropy in the ground state. Okay, so there's some ground state properties that you can measure in a system with anionic excitations so that you don't have to create the excitation itself, but you can detect them in the ground state. Okay, so you have to compute this number gamma, which tells you whether you're in the topological phase. You have to construct this combination of entanglement entropies and subtract them. And so my student John came up with a very interesting method to measure entanglement entropy. So there's previous work by Melko and Hastings. It turned out that that had to be modified for this problem. And so his idea, very briefly, was if you want to construct the ratio of these partition functions of entanglement entropies, what you can do is you can create a fictitious field, a magnetic field, so that when lambda is 0, you get the numerator, and when lambda is 1, you get the denominator. So it interpolates between the two. And then rather than simulating actually this numerator and denominator, you simulate an ensemble in which lambda is finite. And then it turns out that this gamma actually has a very nice Monte Carlo estimator that you can write down. And you have to just calculate an integral over this ramp over lambda. Actually, he went even further. He used this idea of Jasinski, in which you can actually calculate the difference of free energies in some non-equilibrium protocol of ramping lambda. But in this simulation I'm going to show you, we just use the So this is the A and the region in which you do a trace to. Yeah, so it's at the Pants construction where you sort of trace over the. So you have a simulation which is technically 2 beta in this, and here it's simulated, it's traced off at half the beta. So now you want to calculate the ratio of this to this. So this guy has also these gray regions which are also traced. Yeah, and then you do the integral. So here's the data. So here's again we're showing as a function of n. We're showing how this. So technically in a finite system there have to be two plateaus corresponding to the electric charge and the magnetic charge. And it's kind of hard for us to see the second plateau because there are equilibrium issues. But I'll show you that we have some data for the second plateau. So all of this data is very well equilibrated. And here you can see that before n reaches its threshold, when you're in the long loop phase, the topological entanglement entropy is 0. But then it goes to this quantized plateau and you exceed it. And here's some finite size scaling. This is all for L equals 8. This is 8, 12, and 16. So it's 8 cross 8 times 3 and 16 cross 16 times 3 to get the Kagome lattice. And this is John's work showing the quantization of the topological entanglement entropy. And so here, he's showing how if you can even see the second plateau almost, but there's an equilibrium. There's a problem with equilibration. You go to very low temperatures, but this is pretty convincing evidence that this thing is a Z2 liquid. So this is the amount of time I have left. Okay, good. So I just want to conclude this part, and say that we have this very simple model. It realizes a quantum spin liquid. Now, there are a couple of ideas of where it could be realized. One of course is ultra cold atoms, in which lots of models with SUN symmetry. But recently, models like this, it turns out, have also been discussed in the context of graphene. There's a paper by Leon Valence and collaborators where they studied something very similar. I should maybe go to the next part, and maybe in the question answer I can tell you how this model arises in that context. It's a perturbed version of this model. So the second part is about these exotic valence bond solids. And so by way of introduction, we all know the spin half antiferromagnet. If you think about the Heisenberg antiferromagnet spin half, if you look at this interaction, there are two ways you can think about it. One is that it's again a projector onto singlets, so the system will form some dimerized state, or you can think of it in a semi-classical way, and then you might think, okay, the spins point up and down. Of course, very interestingly, the system does a combination of these two in some sense. It goes into this very exotic SU2 level 1 WZW theory. And it has an emergent symmetry, which you can rotate the nail vector and this VBS vector. And this is a very interesting thing that Hans Bethe initiated, and then I think maybe 30, 40 years later was, so I think he originally solved the ferromagnet, but 30, 40 years later, people solved the antiferromagnet. So it's a long, rich history of spin chains. They were first proposed straight after the discovery of quantum mechanics. So now you might think, okay, so there are these two tendencies. So if you increase the value of spin, the system maybe becomes more semi-classical, and then you should get something that's more nail-like, but actually you don't. We all know that when you take the spin 1 chain, you get this interesting AKLT ground state, and you have these edge modes. So all of this was synthesized in some sense by Haldane in his important work, where he showed that there's a way to think about this in the context of topological term. So this, of course, was recognized by the Nobel Prize a few years ago. But I just wanted to emphasize that very important in the back of Haldane's thinking was this exact solution of the Bethe chain. So given this, one could ask, what about 2 dimensions? So in 2 dimensions, we can't use Bethe ansatz, but we can use Monte Carlo. And so it's a lot of interest to ask, what is the effect of the value of spin on the ground state of 2-dimensional antiferromagnets? So of course, if you just take the Heisenberg model by itself, it's always nail-ordered, and this is accepted without any doubt now. But it's been recognized that actually the value of the spin plays a very important role when you disorder the antiferromagnet and at critical points. So given this motivation, it's interesting to ask whether we can write new models down, so we all know the Heisenberg model doesn't have a sign problem, but whether we can write new models down for spin S spins which don't have the sign problem. So we figured out a way to do that, and there was one problem that we applied it to. Okay, so first of all, let's just look at the disordered states that you can have where you break nail order. So for spin half, you can have the columnar VBS, and of course, the transition between nail and this columnar VBS has been a topic of a lot of interest, something I've worked on too, but I won't tell you about today. And there's lots of interesting, in fact, I had some slides if someone's interested, but I skipped over them in this presentation because I don't have much time. But if you take spin 1, you can have something very interesting, which is called the Haldane nematic, which we call the Haldane nematic, but I think it's maybe called other things. And the idea is that if you have a spin 1 system on a square lattice, it can form Haldane chains spontaneously. And we call this a nematic because it's sort of like a lattice nematic. It breaks rotational symmetry, but it preserves translational symmetry completely. Okay, so one of the goals of this study was to find a sign problem-free model that realizes this. I'll show you, there was this work by Fa Wang, who's here, and Kivelson and Donghai Li, that argued that the transition between the nail state and this Haldane nematic could be continuous and is exotic O4 model with theta equals pi. So in order to study this idea, we need a sign problem-free model that realizes the Haldane nematic. And I'll show you that we found this model and we're able to study this transition. And of course, we also have now a sort of a nice algorithm that can generate many of these models. So we hope that we'll find more interesting things too. Okay, so maybe I'll just be really brief on this because there's technical details about Monte Carlo, which I'm not sure everyone's interested in. But the idea is basically, it goes back to Todo and Kawashima. And the idea is to write a spin S as many small spins and then use a symmetrized. So if you modify the boundary conditions, you can make this small spin system a faithful representation of the spin S system. So it's like you have an infinite ferromagnetic interaction as a boundary condition. Yeah, so I'll skip over the details of this, how we come up, but we basically come up with an interaction which I can write down. It's a bit complicated. And this interaction, I'll show you, realizes a Haldane nematic. So now if we supplement it with the Heisenberg model, we can actually study the phase transition between the Néel and Haldane nematic in this model. Okay, so now the interesting question is, what is this? Is this phase transition continuous, and is it a realization of this O4 model at equals pi? Okay, so first let me show you that we do have a Haldane nematic. You can measure the conventional VBS order parameter, which is Fourier transform at pi 0 of the bond correlation function, and then so that I call that order parameter phi. But there's another order parameter psi, which is the difference between Bx and By. So this is like an Ising order parameter, and this measures rotational symmetry breaking in the system. Okay, so now if you do finite size scaling, you can sort of establish this phase diagram. So we've spent some time doing this in a careful way. But here I just show you some representative points to show where the Néel order parameter is finite and where this psi order parameter is finite, which is this Haldane nematic order parameter. The phi order parameter, which is the VBS order parameter, is just 0 everywhere in this phase diagram. So there's no VBS. So with spin ones, you could have a VBS, but it turns out that it's not found in this phase diagram. Okay, so now we can study the phase transition. So if we study the phase transition in this region, it turns out that this is a very nice Ising model. So this shows the histograms of the order parameters. It's the textbook example of a phase transition. You have one peak that splits into two peaks. At the phase transition, you can collapse the data very nicely with Ising exponents. So the transition is continuous and of the Ising type over here. Then the question is, as you go down over here, especially this red region over here, where the transition remains continuous. Okay, so in our model, we find that the transition is not continuous. So it begins continuous, and then at some point, there's presumably a tricritical point, and the transition becomes first order. So this is at very low temperatures, and so we conclude that basically this quantum phase transition between Néel and Haldane nematic actually is first order in this model. Okay, so yeah, I hope I didn't speak too fast, but So I didn't have a chance to tell you about the algorithm, but the algorithm is quite general, and there are lots and lots of models we can write down with spin S. And so they're interesting because there are lots of new phases that you can realize with spin S, which you can't realize with spin 1/2, including a quadrupolar phase, this Haldane nematic, and possible spin liquids. And so we're spending a lot of time thinking about the phase transitions between models. Okay, I'll stop here. Thank you.
Questions?
So, Ribhu, so for the first part,
Yeah.
so the detect the Z2-Topological order, so you measure the entanglement entropy. But what if you just measure, let's say, the energy of the system as a function of temperature, or the specific heat as a function of temperature? Probably as you go down in temperature, you should also see that the energy scales associated with the two types of topological excitations.
Yeah, so there should be two gaps.
In
principle, yeah. So there should be some activated.
Yes.
I think we saw that.
I see. We actually did that.
It's hard to separate the two out there.
No, but I saw your scale is quite, I mean, one is beta equals 10, one is around 100. So it's actually quite separated.
Yeah.
I mean, we did that for the BFG model, which you can see the energy scale.
Oh, I see.
Yeah. Actually, that's very, it's not as direct, but it's actually a suggestive evidence.
I see, yeah. Thanks.
So if there are no more questions, let's thank the speaker.